In this lesson, we'll take a look at combining functions by adding them, subtracting them, multiplying, and dividing them. Okay, and very simply, we're going to look at some new notation just in terms of how you express these combination functions. So if we're adding or subtracting functions, you can simply take f of x plus or minus g of x. If we're multiplying functions, it's going to look like this, and we can simply multiply the two functions together, and same with division. Okay, so we're going to look at two different approaches to how to figure out these equations, and we're going to pay some particular attention to the domain. So we'll start with just an algebraic approach to combining functions. So in this first example, we have a linear function right here as our f of x, and we have a quadratic function as our g of x. And we're just going to develop an expression for each of the following. Okay, so in our first example, this is f plus g, which means we're taking f of x plus g of x, and of course that would equal 3x minus 2 plus x squared plus x, and then we would just simplify that. So I think you can see that we end up with a quadratic. So we added a linear function and a quadratic. We ended up with a quadratic. And just taking a look at the domain, please note that the domain of the original linear function, of course, was all real numbers. Domain of the quadratic was all real numbers. And the domain of the resulting quadratic is also all real numbers. And hopefully that makes sense. Okay, so do yourself a favor, pause the video, and do g minus f and see if you can do that. Okay, so there you have g minus f, also results in a quadratic, and of course the domain of that is all real numbers. And we're just using our knowledge of functions to help us to see that. Okay, so in example 2, we're going to try the same thing by looking at multiplication and the division of functions. And again, f of x is linear, g of x is quadratic. So we'll start with f times g. So of course that's f of x times g of x. So that would be 2x plus 3 multiplied by 2x squared plus x minus 3. And I'm asking for it in standard form, so go ahead and pause this video and expand that out yourself. Okay, and hopefully you agree with me. And note, this time we actually have a cubic function, but the domain is still all real numbers. Okay, so hopefully you remember from all of your work this year that all polynomial functions are all real numbers. Go ahead and try to do f divided by g by yourself. Okay, so you can see in working with f divided by g that you end up being able to cancel out a 2x plus 3 factor in both, and so the function simplified becomes just 1 over x minus 1. So remembering our knowledge of rational functions, you will recall that this is a rational function with a whole, okay, and it also has a vertical asymptote at x equals 1. So note here, we took two functions where the domain of both of those functions was all real numbers. However, f divided by g, the domain is not all real numbers. So we have to consider the discontinuities in the resulting rational function as well. Okay, so in this one, we would say that the domain x cannot equal negative 3 over 2. That's where the whole exists, and 1, which is the vertical asymptote. So when we do divide functions, we have a little bit extra that we need to consider. So next we're going to move to a graphical approach, and there are two methods that we consider for graphing the sum, difference, product, or quotient of functions. So one of them, of course, based on the examples that we saw on the previous screen, would be to determine the equation algebraically and then just use our knowledge of functions to go ahead and graph the polynomial or the rational or whatever it is. Okay, and that would be the easiest if they're functions that you are the most familiar with. And then the other method is what is called the superposition principle. Okay, so that is a term that you would want to know. And that basically involves adding or subtracting or multiplying or dividing the y values together, whether it be in a table of values or on the actual grid itself. And sorry, this should say or multiplying or dividing any of the operations. So in example 3, we're going to use the superposition principle to sketch the graph of f plus g, okay? And we're going to look at the domain. And these are just not functions necessarily we know, but just based on the graphs that we see. So the first function, let's say that red is f. Let's say that green is g, and we're going to look for f plus g. And before we even do that, let's just set up over here where we can talk about our domain, because already we can see that the domain of f, if you like, is from -4, right, is less than or equal to x, is less than or equal to, that's our 5, right? So 5. Just labeling our graph. And we can see that the domain for G is -7. X is between -7 and 6. Okay, so just looking at it in general. So basically, we're just going to go along all of the various x values where the functions are defined, and we're going to add red plus green. And the good news when you're adding is the order doesn't matter. Obviously, if you were subtracting, you would have to pay a little bit more attention to what you were trying to do to add them. Okay, so I'm going to start at sort of a little bit of a simple place. I'm going to start at the right here. You'll notice right here for the g function at 6, I have nothing to add it to, right? So it's like saying that I'm adding the y value. So I'm adding 3 plus nothing, okay? I have nothing. It's not defined, so I actually can't add them together, okay? Moving to the left, so at x equals 5, I'm going to look. I'm adding 4 plus 1.5 gives me 5.5. So I have that point right there. Okay, and I'm not going to do every single point, but I'm going to go ahead and look for some nice values. Okay, next I'm going to go at x equals 4. I'm adding 0 plus, let's say, 3.5, and that's just 3.5. Okay, so there's a difference, of course, between adding 0 plus a number versus nothing plus a number. We can't do that, okay? Moving along, I'll move to a little bit more left. Here we have to be a little careful. Again, doesn't matter, thankfully, the order that I'm adding in. So approximately 2.5 plus -1.5. So 2.5 minus 1.5. 2.5 minus 1.5 takes you somewhere around here. Okay, let's look at x equals 2. Here I'm adding 2 plus -3 is -1. Okay, let's look at x equals 1 right there. Here I'm adding 1.5-ish plus -2. Brings me to about here. Okay, and I'm not sure if you can see where we're at so far, but just joining up the points with a nice straight line, because that's what f and g were. Use your ruler, of course. Okay, I think you can see that that's where I am so far. So do yourself a favor, pause the video and see if you can keep going on your own. And again, we're just approximating, but this would be a nice straight line here. Okay, like I said, use a ruler. I'm going to look at this last one. I have a 1 plus -2 brings me to there. Okay, so those blue open circles are just me showing you, but hopefully you can see that this is f plus g. Okay, and I can't continue it all over here because I have nothing to add the green to. Okay, so in other words, the domain of f plus g is between -4 and 5. In other words, what we say is we say that the domain is the intersection, or the domain part that is common between the functions f and g. So the domain of f plus g is the intersection of the two domains of f and g. And that is true when we're adding, subtracting, and multiplying functions. Okay, and now I just want to take a look at what happens when we divide functions again. Okay, so in example 4, again, I have two linear functions, f and g, and we are going to take a look at g divided by f. And of course, that would be g of x over f of x, and yes, the order is going to matter, so that would be x minus 1 over x plus 2. And we know from our knowledge of functions that that's a nice, fairly simple rational function that you should easily be able to graph. So you're not going to use the superposition principle here. You are going to come up with the equation, and then you're going to use all of your properties. Okay, so let this be a good reminder in terms of putting things together as well. Let's go ahead and state the 5 characteristics of this function. Okay, so there we have our characteristics, and then in order to graph it, we would need to do our testing for our horizontal asymptote and our vertical asymptote. So go ahead and pause the video and try to do that on your own. Okay, and so when we go ahead and put it all together, let's try to graph it. Okay, so when we go ahead and graph it, we see that we end up with something like this. And I think you can see from the domain here, again, with dividing, the domain of the original two functions f and g was all real numbers. However, when we divide, we have those additional restrictions, and we know that the domain here is all real numbers except for -2. Okay, so we have extra considerations when we are dividing functions. Let's try one more example together. And so in this last example 5, I want you to note f of x is just a linear function, x. G of x is sine x, is a trig function, and we're going to look at the multiplication of the two. So f times g here, algebraically, would just be x sine x, and we have no idea what that looks like. So we can't just find it algebraically and graph. Here's where we're going to need to use superposition principle, and in these cases, I find it much easier to just lay it all out in a table. Now, the only thing that's extra challenging about this one is note when we've been graphing sine x all throughout the year, we've been using radians for our x-axis, right? So pi, 2 pi, but don't forget that that's just 3.14 and 6.28 and so on. So here we can choose any x values to put in our table, and so I recommend using radians for that to make this make sense to you. Okay, so I'm going to choose the values from -2 pi to pi. Okay, and f of x is just x, right? So y just equals x. So our f function are really just the same values, but instead of writing them in radians, it will really help you out a lot if you take this opportunity to write them in decimals, because we are going to be graphing this. 3 pi over 2 is 4.71. We know that this is 3.14. Pi over 2 is -1.57. Okay, so f of x is just x, so that's why I'm graphing that. That's why I'm writing the same values. Okay, and then we know our sine values at these places as well. Sometimes it might help you to start here at 0. We know the sine of 0 is 0. Then we know it goes up to the maximum, comes back to the axis, goes down to the minimum, back to the axis, right? And then I'll work backwards here. We have our -1, 0, 1, and 0. Okay, and hopefully you can see that to get the f times g column, you are simply going to multiply those two y values together, right? Okay, so this is the same as doing it on the graph, although this is a little less confusing, especially when it's tricky here. So we're going to multiply to get f times g. So I'll give you a minute, pause the video, and please do that. Okay, so there we have our values in the table, and first thing I'm going to do is just go ahead and set up my grid. Okay, and of course I've designed this grid to work out perfectly for you in this example to get this idea across. One thing to note that when your x scale is in radian values, remember though that just means 3.14, 6.28, your y scale doesn't have to be the same, right? So you're going to choose those appropriate for your graph. So I'll give you a minute. Go ahead and plot those points. Hopefully it's clear to you that you are plotting your x values and your y values, and then see if you have an idea about what this looks like. Okay, so there's what I have for my points. And it might be hard to figure out what it looks like, but through practice, you can definitely get a sense of what it looks like, but also remember what the sine wave looks like, right? It continues on and it's periodic. And so this is a nice smooth curve, very similar. Of course, it continues. It continues in both directions. And actually what happens is you can see if you continued on in the table, and you can take a look at this on Desmos, y equals x sine x, and zoom out, and you'll see that it just continues on as a wave, and the max and mins or the bumps get bigger and bigger and bigger, okay? So a couple of things I want you to consider as sort of the final thought. Okay, the domain of f plus g, f minus g, f times g is just the intersection of the two domains as we talked about. Okay, so they're only defined where those two domains of f and g overlap. If f and g are polynomial functions, then the degree of the sum or difference of the two functions is less than or equal to the highest of the individuals. That's just a side note you could figure out on your own. It's not always possible to graph the resulting equation when two functions are added or subtracted or multiplied using the techniques that we've learned, and so this is where the superposition principle is used. Okay, and the last and I would say the most important note is just to consider that the domain of f divided by g is the intersection of the domains of f and g, but there's an additional restriction because there would be any values where g of x equals 0 would also be a restriction in the domain. Okay, so go ahead and practice some of that.